Good morning, Santonio. How are you? Morning, Bella. Morning, DJ.
Dude, Mr. Dunn.
Yes, DJ.
How did you change your background? How do you guys change your background?
You go to video. I think the option is stop under the arrow next to stop video, and you can choose virtual background.
Okay.
Good morning, Jonah. Morning, Dahlia.
Hi.
How's everyone doing today?
I'm pretty good so far. I'm tired.
Did you sleep too long or not enough?
Too long. I just woke up like 10 minutes ago.
See, telling you, get that schedule down. How's it going, Julio? All right, while we're waiting for folks to arrive, go ahead and do the bell work in the chat. You can privately message me, or you can respond to everybody if you want.
Tired, man. Did it to myself.
Morning, Christian.
Tough.
Good morning, Victor. Go ahead and do the bell work in the chat, either individually to me or to everybody. All right, take another 30 seconds. All right, looks like most people have a really good read on how to do this. And this should look familiar because why? Where have you seen this very recently?
On the test.
On the test,
On the
awesome.
Activity sheet. Anywhere else?
Yeah, all right, so let's go ahead, take a look at the test because that's what I said we were gonna go over today. And we might not even have time to go over the whole thing, but I'll stay on, and if folks can stay on as well past noon, then I'll make sure to go over as much as I can. Let me see if I can. Does that make it easier to see?
Yeah.
All right. So I did not provide formulas on the test as you saw it yesterday, but I did put some of those on for our discussion today. We are going to need most of those formulas as we move through, but let's talk about the conceptual parts first. So, like I said, I want to see all your work. You'll get full credit if I see your work because I am going to be going through the answers. But we're looking at numbers 1 through 6, and we're looking at these 3 carts. So we have these carts, these 1 kilogram carts. Good morning, Vivian. And we see that a force is applied acting to the right. We are assuming that friction is 0, so we don't have to worry about that coefficient of friction. And then for each question, one or more of the features of the system has been changed. You're supposed to indicate what effect the change will have on acceleration. A, B, C, or D, greater, less, remains the same, or not possible. All right, so the number 1, the towing force is increased to 0.55 newtons. So this force is increased. What's that going to do to the acceleration?
It will be greater.
It will be greater. Excellent. So, and we can prove this, all right? Towing force, so if F equals ma, if F increases, then something over here has to increase too. Okay, so we can't increase the mass, but we can increase the acceleration. So increasing the force will increase the acceleration. All right, the weight of the cart is 9.8 newtons. So what's the weight of the cart right now?
1 kilogram.
Weight equals mass times what?
Acceleration.
And the acceleration is due to what?
Gravity.
Gravity.
Gravity. And if we take gravity to be 9.8 meters per second squared, 1 kilogram times 9.8 meters per second squared gets us what force?
Normal force.
9.8 newtons.
9.8 newtons. So if the weight of the cart is 9.8 newtons, does that mean the acceleration will be greater, less, or remain the same?
The same.
It is the same. All right. Oh, Aisha snuck on too. Hi, Aisha.
Hello.
Who said hello?
Aisha. Aisha said hello.
That was a very radio voice hello. I did not recognize it. Okay. So that is just saying, hey, the weight is 9.8 newtons for number 2. Okay, so what if we double both the mass of the cart and the towing force? So let's say right now we know that the towing force is 0.5 newtons and the mass is 1 kilogram. So let's just calculate the acceleration right now so that we have a number for acceleration. So 0.5 equals 1 times what?
Wait, what you said?
9.8.
So F equals ma. In this case, the force is 0.5 newtons. The mass is 1 kilogram. So 0.5 equals 1 times what?
9.8.
8 meters per second squared.
0.5, I'm just asking for math right now. 0.5 equals 1 times what?
Oh, you got to divide.
Well, okay.
0.5.
Uh-huh. Acceleration equals force divided by mass. Let's do it that way. So our acceleration is our unknown. 0.5 newtons divided by 1 kilogram. 0.5 divided by 1 is what?
0.5.
0.5 meters per second squared. So that is our current acceleration. But if we double both the mass and the towing force of the cart, let's double the towing force. What's double 0.5 newtons?
1 Newton.
1 newton. Let's double the mass.
Oh, it's the same.
Kilogram.
2 kilograms. So what's the acceleration? 1 newton divided by 2 kilograms. What's 1 over 2?
0.5.
0.5 meters per second squared. Did anything change? Did anything change? The acceleration
That's late, this
remains
test.
the same. All right. Okay, so the 0.5, so number 4, the 0.5 Newton towing force is applied at an angle as shown at right. Remember, yesterday we had a very similar problem that we worked out. And you can visualize that if you're trying to, oh, I have something here as a visual aid. If you are trying to pick up this multimeter, for example, and we're trying to drag it along a surface, don't mind this is a demonstration from earlier. We're trying to drag this along a surface, and we pull it completely horizontally. That will require less force than if we're trying to pull it along at an angle. And it will require even less force than if we try to pick it straight up. Because now we're feeling the full gravity of that object. So this on the horizontal requires the least force of all. So what that means, get to the right one. Okay, what that means is that if we apply it at an angle, what is that going to do to the acceleration if we're using the same force? Is it going to go faster or slower?
Slower.
It's going to go slower. So in that case, the acceleration will be less.
Ooh,
right.
I did good.
Number 5, the coefficient of friction for the cart on the track is 0.05, meaning there is friction. If there is friction for that cart, what's that going to do to the cart?
Gonna go slower.
Slow it down. All right, so then you would have the acceleration be less. Finally, we have the track is inclined as shown below. An inclined track meaning that you are going to have to, you're pulling against gravity, right? Gravity is working against you. So if you're pulling with the
Yes.
same force, what's going to happen to the acceleration?
Going to
Less.
decrease.
It's going to go down. It's going to decrease. The acceleration will be less.
Okay, I understand.
All right. So numbers 7 through 10, we've got a velocity time graph. Now, this seems like a blast from the past at this point because probably the last time you've seen one of these was a couple months ago. But we can't forget any of this stuff because everything that we're talking about builds on previous knowledge. So we're looking at this train. The first thing that I want you to do, as always, is I want you to explain what's happening in any sort of velocity time, position time graph that you're given. Explain it in your own words. So what we see here is, let me get my little spotlight. What we see is that the train has a certain velocity, a high velocity. And between points A and B, what is happening to that velocity? Between points A and B, what's happening to that velocity?
Decreasing.
It's
Increasing.
decreasing.
Oh.
The train is
Oh.
slowing down. But notice that it's still moving because the velocity is well above 0. Okay, so the train is slowing down between A and B. And then between points B and C, we see that the train is what?
Not moving.
It's not moving? Look
No,
at
it's
the velocity.
moving at
The velocity
it's moving constantly.
is moving at constant velocity. Excellent.
Oh, well, I said that first.
All right, I got you. So between points C and D, what is happening?
Decreasing.
The velocity is decreasing, so it's slowing down. And at point D, how fast is it moving?
It's not.
It's not. It slows down to a stop. All right. So now that we understand that part, we can hopefully draw our position time graph and acceleration time graph. And we're just worried about what happens between points C and D. All right. So the trick is, what is happening between points C and D? As time goes on, is the position increasing or decreasing?
Decreasing.
So it's going backwards, the train's going backwards?
Hold up.
Can you say the question again?
Between points C and D, what is happening to the position of the train?
Slowing. Wait.
All right, so let's demystify a little bit of this. Let's take it from point B, all right? Between points B and C, remember what's happening, what's happening, what's the velocity? Is it changing, is it staying the same?
It's staying the same.
Staying the same. This is a constant velocity right here. So in other words, position time graph from point B to point C is going to be a straight line going up,
Oh, I knew I should have did it like that first.
okay? Now you don't have to do this. I'm just doing this so that we have a reference point. So in other words, I lost something. The position is increasing as time goes on. Now between points C, and I'll draw in D right here, between points C and D, is it still moving in the same direction? The velocity is decreasing. Is it still moving in the same direction?
Yes.
Yeah. Still moving in the same direction. But since the velocity is increasing, what's happening is that position is not increasing as fast. And eventually, because the velocity goes down to 0, the position eventually flattens out. And this is showing what happens when the velocity is 0. So what we
Acceleration is
see
0.
is that the velocity is decreasing right here until the velocity hits 0. Okay, so what I wanted to see was between position C and D, this curve right here. That's what I was looking for. All right. Now we have the acceleration time. So this is a little bit easier to get out of this information because what we know is that if the velocity is staying the same, what's happening to acceleration? Is there any acceleration if velocity is staying the same?
No.
Nope. So if I were going to draw from point B, 0 acceleration. And then what happens at point C? And we'll go from point C to point D here. What's happening to the velocity?
It's a decrease.
Decreasing.
Decreasing. So what does that mean about the acceleration? Is that a positive or a negative acceleration?
Negative.
Negative.
Negative acceleration. And we can put that dashed line in there to show how that acceleration. Hello.
Whoa. Wow.
Is that you, Aisha? All right. You can unmute yourself, but make sure you're not making noise on the line. All right. So we see that that acceleration went from being 0 down to dropping to a negative acceleration. Questions about that? I am not hearing or seeing any questions.
Wait, I do have a question.
Oh,
Not
yeah.
about this in particular, but just about assignments in general.
Okay.
For like drawing and stuff like this, should we do it on a separate sheet of paper? And like,
However you would like to. If drawing on a separate piece of paper makes the most amount of sense and then scanning it, then I think that's a great idea. If, on the other hand, you would like to do everything digitally, then it's completely up to you.
okay.
Any way I can receive it, I'm happy.
I have a question.
Yeah, go ahead, Victor.
How do you actually draw in the graphs on the document?
For this one, because this isn't a Google drawing, you could copy this image and you could go ahead and go to Insert, Drawing, and you could say New. And then you could go ahead and make your drawing in here. We can make a couple lines. There's your axes. And then you could make a curve or a scribble. You do something like that.
Mr. Denton,
That's me.
what if I when I did the position versus time graph, what if I made it like an L shape?
An L?
Yeah, but like curved.
Well, it all depends on how that curve is looking. The curve for number 7 for position time would have to be like that. So let me actually draw that out instead of just waving the mouse in thin air. The curve needs to look more like that. If it's like this, it does need to be a curve, right? If it's like this, that's incorrect. That would be
No, like started from the top of the X graph and then.
You can draw on here. Show me what you're talking about.
Wait, how do I do that?
You have drawing.
There's a little pen, like pencil icon thing.
Yeah. Annotate. If you hit the annotate button.
Oh. And I think that's right. Yeah.
Got it. Nope, that's incorrect because
Ooh.
no, because the position is, that's showing that the position is decreasing over time, but in fact the train is moving forward, so the position is actually increasing over time.
Oh. Oh, okay.
Okay. All right. So then we have for the interval from C to D, we saw that the train was doing what?
Slow down.
Slowing down. Is the net force on the train negative at any time? Is the net
No.
force
Yeah.
acting, is the net force acting in the opposite direction of the motion? I would say yes, because it's slowing down.
Oh.
Ooh, I got that right. Good.
And then the net force on the train, the largest, if we look at this graph here, here the net force is negative and it's small. Here the net force, because it's moving at a constant velocity, the net force is 0. And here the net force is negative, but it's large because it's slowing down a lot. And so the net force here, you could say the net force is largest here, right? But if you interpreted that as like the largest, like 0 is the largest because these two are negative, then I would also accept between B and C. As long as you justify your response by saying why you consider it to be the largest. All right, let's move on to 11. I think we'll get through this one before noon, and then if you want to stay on, I'll continue with at least through number 13. So number 11, an Olympic bicycle sprinter with a mass of 70 kilograms, including the bicycle. That's about 154 pounds. Can go from rest to a speed of 15 meters per second in 3.2 seconds. By the way, that is an insane acceleration. All right, but let's figure out what that net force is. So what's our formula for net force?
F equal MA.
Good, we can start with F equals MA. We don't have any friction, so we don't have to worry about including any frictional component. So we're trying to determine the force. What is the mass of this bicyclist?
70 kilograms.
70 kilograms. Now, how can we determine acceleration?
Velocity equal acceleration time.
Velocity equals acceleration what?
Times time.
Times time. Okay, we do not have an acceleration. We do have a velocity and we have a time. So how can we determine acceleration from velocity and time? What do we need to do to this formula?
Plug in velocity and plug in time.
We don't have
First.
Right. But how do we have to rearrange this formula in order to get it equal to acceleration?
Velocity divided by time.
Good. Divide time by both sides. So what is the velocity of the bicyclist?
15 meters per second.
15 meters per second. And then we're going to divide that 15 meters per second by
3.2 seconds.
3.2 seconds. Quick math. Who's got this?
4.69 meters per second squared.
All right. Let's keep, right now we only have 2 significant figures, so we're going to do 4.7 meters per second squared. That is our acceleration. So we can plug it back into here. So we have 70 kilograms times 4.7 meters per second squared. How many newtons of force is the bicyclist?
Somewhere around 328 newtons.
329 probably.
Sounds good.
Ouch.
About 300, and actually, right, we have only 2 significant figures, so that rounds off to 330. 330 newtons sounds good to me. All right, as I said, if you want to view this later at on your own time, it is noon, but I'm going to continue through 12 and 13. All right, so we've got the block on the surface below. The coefficient of friction, mu, is 0.30. So we have a situation where the force is pulling this 2 kilogram mass to the right. And we're told that the applied force is 21 newtons. We're asked what the acceleration is. What formulas do we need in order to determine what that actual acceleration is?
You need F equal ma. F of k equals mu times normal force F(n). Oh, yeah, that's it.
Good. And we're going to need something else, right? Because that's going to tell us what the frictional force is.
You need the net force equals force applied minus frictional force.
Excellent. So a lot of physics ends up being making sure that you're choosing the right formulas. So we know that we know the applied force, right? So we are looking for the, whoops, wrong button. We're looking for the net force. What is the applied force? What does it say in here is our applied force?
21 newtons.
21.0 newtons. And then we want to add that to the frictional force, which we know is mu sub k. And you may have a question at this point. Why mu sub k and not mu sub s? It doesn't really matter for what we're being told. We don't know whether this is static friction or kinetic friction at this point. We can probably assume that it's static friction because we're not told that it's already moving. But honestly, it doesn't matter because it's still the frictional force is going to be dependent on both the coefficient of friction and the normal force. So we have a mu sub k, we have a frictional coefficient. What is that coefficient of friction?
0.30.
0.30. And we have a normal force. How are we going to determine that normal force?
F equal ma.
Well, good. What is the mass?
2 kilograms.
2 kilograms. And what is the acceleration?
9.8 meters per second squared.
Awesome. So we have all of our numbers. There's one more thing we need to do though. Is the friction acting in the same direction as the motion, or is the friction acting in the opposite direction of the motion?
Opposite.
Opposite. So we need to make sure
Negative.
we subtract that frictional force. All right.
Oh, thank God.
This, from this point on, is just a question of plug and chug. All right. So 0.30 times 2 times 9.8 is going to be somewhere around 6.
5.88 newtons.
All right. We have two significant figures. So that
1.9.
means that's going to be 21.0 newtons minus 5.9 newtons, right?
If I didn't do that, does it still count as wrong?
Yes, it's all wrong. No matter what you did,
What?
it's all wrong. No, I'm just kidding.
Oh,
If you didn't do what?
the what you doing? The significant figures.
I want you practicing significant figures. I want you to make sure that this is something that you're getting in the routine of, but I am not taking off points unless
thank God.
it impacts the quality of your answer. So let's do the math on this. I get 15.1 newtons. Is that right?
Mm-hmm. Mm-hmm.
All right, so that is the net force. Remember, this is asking for what?
Acceleration.
All right, so F
Equal ma.
equals ma. Our force is 15.1 newtons. What's the mass?
2 kilograms.
2 kilograms. It doesn't say 2.0 kilograms, which is kind of a killer here. We don't, but we're going to assume that it's precise, because otherwise, why would they tell us 2 kilograms? All right, and then this is going to be multiplied by acceleration. So to solve for A, I'm just doing some math over here, just some algebra, taking that force and dividing it by the mass. What do you get?
Oh, wait a minute. 7.55.
With two significant figures, we have 7.6 meters per second squared. Any questions about that whole calculation? The great part about these being recorded is that if I go too fast, it's all up on YouTube. I don't know if you saw that yesterday, but I threw everything on YouTube. I gave you the link. I'm going to do that every day. So if I go too fast, or if I go too slow and you tuned out and you're just like, wait a minute, I need to tune into that part. You can always go to YouTube, go through the video, search for the relevant part. All right, so part B, how fast will the block be moving if the force is applied for 6 seconds? So how fast? What kind of thing are we looking for? How fast?
Velocity.
Velocity, awesome. And we know that velocity equals what times what?
Acceleration times time.
So acceleration times time. What's our acceleration from part A?
7.6 meters per second.
Awesome. 7.6 meters per second squared. And then we're going to multiply that by what time?
6 seconds.
6.0 seconds. So if the force is applied for 6 seconds, then we're going to get a velocity of 6 times 7.6, which is somewhere around 46. Someone do the math before I do.
$45.6.
Awesome. And we have two significant figures on this multiplication, so that's going to be 46 meters per second. pretty fast. It's very fast, actually. It's about 140 feet every second. All right, how far will the block have traveled during this 6-second period? This is in the Wayback Machine now. Displacement equals what times what?
Velocity and time.
Velocity times time. We have our velocity of 46 meters per second. How much time passed while it was traveling 46 meters per second?
6 seconds.
6 seconds. So if we do 46 times 6, how many meters will it have traveled over those 6 seconds?
273.
All right. Now, is that our final answer? I actually get 276. Is that our final answer? So was it traveling? I guess what I'm asking is, was it traveling at 46 meters per second that entire time? Did it start traveling? Hello? Someone getting beat up? Did it start traveling at 46 meters per second? So I will go ahead and explain that it started traveling at 0 meters per second relative to the end, where it was traveling 46 meters per second faster. So we have to divide by 2 right here in order to get the actual displacement. And the reason we have to divide by 2 is that we're dealing with what it was the average velocity. So the final velocity was 46 meters per second. The starting velocity was 0 meters per second. And so if you want to find out the total distance traveled, then you have to divide it by 2. The reason you have to divide it by 2 is when you look at the graph, it's finding the area of a triangle. So if we quickly go up here to this graph real quick. Whoops. I want to draw. Let me draw. There we go. We're seeing the position increase over time, and we end up with this triangle. And what we're trying to do is actually determine what the area of this triangle is. All right. In order to be able to do that, in order to be able to find out that, and this is a position versus time, this is a velocity versus time. I should have made that clear. So the velocity is increasing, 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 and in order to find the position, we're multiplying the final velocity by the final time, but we have to divide it by 2 because this is a triangle. So that's the graphical way of thinking about this. And, oh, let's clear that. So because we have to take that average velocity, let's divide that 276 meters by 2 to find the actual displacement, which is going to be 138 meters. So that part, I'm sure, tripped up a bunch of people because it is not straightforward, and you got to learn that. You got to remember that little trick about only taking half of that velocity. All right, and I said I was going to go over number 13. I will save 14 and 15 for tomorrow. So here we have, what is this machine called? Remember what is this machine called?
Atwoods, I don't know.
Yeah, Atwoods Machine.
Oh.
All right,
Was this test a grade?
everything's a grade, Aisha,
Oh.
but I'm going through the whole thing with you, so you should have all the right answers.
Mm-hmm.
All right.
So far.
I hope so. Diagram below depicts a frictionless apparatus similar to that used for your Newton's second law experiment. Block A has a mass of 2.5 kilograms. Block B has a mass of 0.3 kilograms. So I will leave it up to you to draw force diagrams for Block A and Block B, but understand that there is an applied force going to the right on Block A. There is the gravitational force and a normal force. For Block B, gravity is pulling it down, and then there's a tension force that's pulling it back up. The acceleration of the system. Acceleration of the system. What is that formula for acceleration of Atwoods machine?
A equals mass squared times gravity divided by mass 1 plus mass 2.
Mass squared?
Is that what they say? Oh, no, mass 2, my bad.
Good. So, and I just want to real quick remind you of why this formula is the way it is. This is the same thing as saying acceleration equals force over mass, which is F equals ma. The mass of the system happens to include both mass 1 and mass 2. The force of the system is simply due to gravity acting on this one mass. So this is the same thing as saying F equals ma. It's just being put into these terms. So we can pretty easily determine the acceleration of the system. If we take m2, what's the mass of m2?
.3.
0.3 what?
Kilograms.
Kilograms times gravity. Hello. Someone's phone's ringing. Gonna mute you for a second here. All right, so 0.3 kilograms times 9.8 meters per second squared. And then what are we going to divide that by? What's M1? Julio, Santonio, Jonah, Isabella, Victor, Christian, Milo. Are people here but not here? You have to unmute yourself if you want to participate. Or leave.
2.5.
Awesome. 2.5 kilograms plus the other mass is. You can also participate on the chat if you don't want to unmute yourself. I'm looking at both. M2 is
0.
Thank you, Julio. All right, so we've got 0.3 times 9.8 I get, with significant figures, I get 2.9 newtons divided by 2.8 kilograms. That gets me, with significant figures, 1.0 meters per second squared. I expect your work, when you show your work, I expect your work to be a little more expanded than this. I'm trying to give you shortcuts here. I'm trying to just minimize the amount that I'm writing. I expect you to show me a little bit more. And so the acceleration of the system would be about 1.0 meters per second squared. And so I'm gonna leave you off here because all you have to do for this one is do what? For if the acceleration, if block B were 0.41 kilograms, what do you need to do for this? Someone explain, please. Yes, thank you, Isabella. So we would switch out the 0.3 with the 0.41. And then you'd simply be able to recalculate these numbers here, and you would get that new acceleration. Make sure that you've done 14 and 15 for tomorrow. We'll go over this, and we will start our new unit tomorrow as well. Have a wonderful and safe day. Take care of yourself, and if you have any questions